Hello everyone. Our project title is Intelligence-Based Generative Model for Programming Language. This project is developed by our team Agadiswaran, Azim Mohammed, Praveen Kumar from ADS department. Our project coordinator is Mr. R. Gopinath, assistant professor from ADS department. The main aim of our project is to create an AI-based coding assistant that can generate, debug, translate, and explain programming code. Problem statement. The main problem we identified is tool fragmentation. Developers and students use many tools separately like code editor, terminal, debugger, and web browsers. This wastes time and breaks concentration. Our project solves this by bringing AI coding help and code execution into a workspace. Objective. Our objective is to build an intelligent backend using fast API and integrate the CodeGen 2B model, which is from Hugging Face. The system can perform code generation, debugging, language translation like Python to Java, Java to C++ likewise, and explain the code. We also focus on performance optimization so the model can run faster even on normal cloud servers. Research gap we identified is existing tools have some limitations. ChatGPT can answer coding questions, but it does not provide a dedicated coding workspace. GitHub Copilot is powerful, but it is mainly for professionals and may be costly. Most tools give code, but they do not clearly explain why the code works. Our project focuses more on learning and understanding. Here I will share about the existing work. Existing systems like ChatGPT, Cloud, GitHub Copilot, LeetCode, and HackerRank are useful in different ways, but they are either chat-based, expert-focused, or limited in AI explanation. So our system combines coding, AI support, and learning explanation in one platform. And move on to the proposed work. In our proposed system, we provide an all-in-one workspace. It includes a code editor, AI assistant, and terminal. The system is especially useful for students because it explains the logic, not just the final answer. It is also lightweight and can work in a browser. And move on to the literature survey. We refer to papers. This slide shows the papers and works we refer to. These studies explain how AI-assisted code generation can reduce developer effort and improve programming productivity. They also show that AI code generation has both opportunities and challenges. Let's move on to the dataset collection. For dataset collection, we used the pre-trained knowledge of CodeGen, which learns from open source code repositories. Along with that, we manually collected 1,000 high-quality samples for generation, debugging, and translation. These samples helped us fine-tune the model for our project tasks. The methods used for data preprocessing are: we clean the dataset by removing unnecessary spaces, comments, and noises. We used byte level tokenization, which helps the model understand code symbols like equal signs, brackets, and operators. This step makes the input clear for the AI model. Future engineering. In future engineering, we added clear instruction before each input. For example, if the task is debugging, we add an instruction like debug this code. We also use the task labels like gen, fix, and trans. This helps the model understand what type of output it should generate. Model development. Our primary model is from Salesforce. So we use Salesforce GoldGen to be multi-model. It is a decoder-only transformer model with 2 billion parameters. It supports multiple programming languages like Python, Java, and C++. We selected this model because it is powerful but still possible to deploy on cloud platforms. And here we come upon with the model architecture. This is the architecture of our system. First, the user enters a request in the front end, such as generate code, debug code, translate code, or explain logic. The front end contains the Monaco editor, which gives you a VS Code like coding experience. After the user submits the request, the data is sent into the backend through a REST API. The backend is built using Fast API. Before sending the input to the AI model, the backend performs prompt wrapping. This means it adds proper instruction and task labels so the model clearly understands the user's request. Next, the processor prompt is passed to the CodeGen 2B multimodel. The model reads the input and generates the recording output. For example, if the user asks for debugging, the model identifies the issues and provides corrected code. If the user asks for translation, it converts code from one language to another. To improve performance, we use FP16 quantization, which reduces memory usage, and KV caching, which improves response speed. Finally, the generated response is sent back to the front end and displayed to the user in the editor or output section. So the full flow is user input, front end editor, fast API backend, prompt processing, code gen model inference, optimized output generation, and final response display. This is all about our architecture. Let's move on to the model implementation. For implementation, we used Python, PyTorch, Transformers, Fast API, and Unicon. The backend is hosted on Render, and the front end is hosted on Vercel. We also use asynchronous processing so multiple users can send requests without slowing down the system. Technical challenges. We faced three major challenges. First, the model required high memory, so we used FP16 to reduce memory usage. Second, the response time was slow initially, so we used KV caching and token limit optimization. Third, we did not have a local GPU, so we used Google Colab for fine tuning. Next, move on to the evaluation and refinement. To evaluate our project, we used metrics like accuracy, latency, and BLE score. Accuracy checks whether the generated code is correct. Latency measures response time. BLE score compares the generated output with our manual gold standard datasets. Initial results was our fine-tune model refinement. After the fine-tuning, our model is improved significantly. Logic accuracy increased from 72% to 91%. Average latency reduced from 4.2 seconds to 1.6 seconds. Syntax errors also reduced, especially in language like C++. Deployment and integration. The backend is deployed on Render and the frontend is deployed on Vercel. The frontend and backend communicate using REST API. We integrated Monaco editor to provide a professional coding experience with syntax and highlighting. In conclusion, our project successfully combines an AI coding model with a web-page coding workspace. We improved performance using FP16 quantization and improved accuracy using fine-tuning. In future, we plan to create a VS Code extension, add voice to code support, and train the model for domains like cybersecurity and mobile development. References. These are the references we used for our project. We refer to Transformer Architecture, CodeGen Research Paper, BigQuery Dataset, Hugging Face Model Repository, Fast API Documentation, PyTorch, Optimization, Guides, and Monarch Editor Documentation. Thank you. This is all about our PPT presentation. In this part, I am going to explain the backend implementation of our project. Our backend is developed using Python and Fast API. Fast API is used to create a API endpoint so the front end can communicate with the AI model. We also use the CORS middleware, which allows the front end and back end to connect without blocking. These are the libraries we needed for this project. The main model used in our project is Salesforce CodeGen 2B Multi. This is a large language model mainly trained for programming language. It can understand and generate code in language like Python, Java, and C++. We load the tokenizer first because the tokenizer converts user input into tokens that the model can understand. For model training, we used fine-tuning approach. Instead of training the full 2 billion parameter model from the beginning, we used LoRa adapters through PFT model. LoRa is useful because it trains only a small number of additional parameters. This reduces training time, memory usage, and GPU requirement. The base code gen model already has general programming knowledge, and our fine tuning helps it perform better for our specific tasks like code generation and code explanation. At this point, I'll show my data set manually I created. Here you can see this data set. It's manually prepared using clear format. Here, prompt contains the user request and completion contains the expected code or explanation. This format is very important because the backend also follows the same structure during interface. For example, when the user asks to generate code, the backend drafts the request as prompt and asks the model to complete it. Because the model was trained in the same pattern, it can produce a more accurate output. Now coming back to the backend, okay, let's move on to the CUDA. If CUDA GPU is available, the model is loaded using 4-bit quantization with bits and bytes. This helps reduce memory usage, so the model can run even in limited hardware. If your GPU is not available, the model runs on CPU. After loading the base model, we attach our trained LoRa adapter weights using PEF2 model. This means our final model is a combination of the original code gen model and our project specific fine-tuned knowledge. Then we set the model to evaluation model using model.eval. Because here we are not training, we are only generating outputs. And here you can see the endpoints. The backend has three main endpoints. The first endpoint is generate. This takes the user prompt and generates programming code. It uses low temperature, so the output will be more stable and less random. And the second endpoint is summarize. This takes your code as input and explain what the code does. Here the temperature is slightly higher, so the explanations are more natural. Here you can see that temperature zero point 0.4. And the third endpoint is run. This execute Python code and returns output. It captures the printed output using string IO. If there is any error in the code, it returns the error message. And finally, we use Ngrok to create a public URL for the backend. This allows our front end to access the backend even when it is running in a collab environment. Overall, this backend connects the front end, train model, and execution system together. It receives user input, prepares the prompt, send it to the fine-tuned code gen model, generate the response, and send back to the output back to the users. This is all about my backend implementation. This is front end of our project, which acts as the user interface for interacting with the AI model. The design is built using HTML, CSS, and JavaScript. The main goal of this interface is to provide a clean and professional encoding workspace similar to modern development tools. On the left side, we have a sidebar with the option like new session, workspace history, and user settings. This helps in managing different coding sessions easily. In the center, we have the main workspace. The top section is divided into two parts. On the left side, we have the source editor. This editor is powered by the Monaco editor, which is the same engine used in Visual Studio Code. It supports syntax highlighting and multiple programming language like Python, JavaScript, C++, and Java. Below the editor, we have the action buttons like run, summarize, fix bugs, and translate. These buttons allow the user to directly interact with the AI model. For example, the run button execute the code, summarize, explain the code, fix bugs, the correct errors, and translate converts code from one language to another. On the right side, we have the output panel, which acts like a terminal. It displays execution results, AI response, and a system message in real time. At the bottom, we have a prompt input section. Here, the user can describe what kind of code they want, like write Python code for Armstrong number. That way, user can ask the model to generate code, and then the generated code is automatically displayed in the editor. All these features are connected using the JavaScript function that call backend APIs like generate, summarize, run, and translate. The front end sends the user input and the backend returns the AI generated response. Overall, this interface provides a complete all-in-one coding environment where users can write, execute, debug, translate, and understand code in single platform.